Namaskar. Today in this lecture series on mechanics, we will study what are cyclic coordinates and what are the consequences of cyclic coordinates. Actually, first of all, we'll see that which coordinates are called the cyclic coordinate. As you know that when we study a dynamical system, then uh, the system may be described in terms of conventional coordinates. And as you know that there is a new type of mechanics, there is a new type of approach to solve the dynamical problems, which is the Lagrangian approach, in which we introduce the configuration space, and the configuration space is specified by generalized coordinates. So our dynamical system, which was described in terms of conventional coordinates, is now described in terms of generalized coordinates in the configuration space. And the characteristic function of the configuration space is Lagrangian. In configuration space, we define a function L, which is given by we take one L. This is the function depending upon generalized coordinate, depending upon generalized velocity, and may depend upon time. Right? Now, there may be the situation that any of the generalized coordinate is not present in L. Here your I is going from 1 to n for a system of n particles, where your n is equal to 3n if there are no constraints. And if I say that in L there is a coordinate first I should write s minus 1, then qs plus 1, and last is qn, q1 dot, q2 dot, q3 dot, qs minus 1 dot, qs dot, s plus 1 dot, in time. Suppose your L is in the form that qs is absent from L, then it simply means that qs coordinate is cyclic. So what is the result? That if L is not depending upon qs, then qs is called generalized coordinate. There are many benefits of these generalized coordinates, because if some coordinates are qs is called cyclic coordinate. This is cyclic coordinate. And with the help of cyclic coordinate, our mathematical calculation become very easy, because there are certain consequences of these cyclic coordinates. As you see on the screen, first of all, generalized coordinates are the coordinates which are absent from Lagrangian. These are also known as ignorable coordinates. The second thing is that characteristic functions which are describing your system are do not depend upon this cyclic coordinate. Simply means that, as I told you, that if qj is absent from L, it is called cyclic. We'll see later that if qs is absent from L, it will also be absent from H. H means Hamiltonian, which we will introduce later, because there is a one way to solve the dynamical problems, that is Newtonian mechanics. Then there is another way which is known as Lagrangian mechanics, and there is another approach known as Hamiltonian mechanics. Hamilton's mechanics, where we define Hamiltonian. So if QS, there is some coordinate QS is absent from L, it will also be absent from H. So where H is your characteristic function of the dynamical system, then H will not depend upon that coordinate. If L is your characteristic function defining your dynamical system, then L will be independent of that cyclic coordinate, that coordinate called the cyclic coordinate. Next is that cyclic coordinate remains conserved when the motion is being taken in that coordinate. Suppose I say that this is some object and this is the coordinate. This coordinate is a cyclic coordinate. Now, if Pj is the linear momentum, then momentum is mass into velocity. There is a result that if there is a cyclic coordinate, then momentum is conserved. I'll show you the proof of this statement, that how the momentum is conserved. So if I take that Pj is conserved, I'm supposing that Pj is conserved. I'm assuming that this is true. This implies that mass into velocity is same, it is conserved. So it simply means if there is a translation, if this body is moving, suppose this body is moving, then it is moving with constant velocity. And since movement is in this direction, what will be its next position? This will be like this, 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 and you will see that this point, if it is this origin point, taken as the origin point, then this is not affected by its motion. It is conserved. So this statement that cyclic parameter remains conserved when the motion is being taken in that coordinate is true. Every cyclic coordinate, for every cyclic coordinate, the integral of motion is obtained. This will be proved later. And another consequence is that momentum corresponding to a cyclic coordinate is conserved. We'll come to the last result, that momentum corresponding to a cyclic coordinate is conserved. There are two other consequences of cyclic coordinate which I'll prove here, and I'll write them as two theorems. So first of all, we'll see how the momentum corresponding to a cyclic coordinate is conserved. You know that Lagrange's equation of motion is delta L delta Qj dot minus delta L delta Qj 0, where L is T minus V. Naturally, we are talking about the holonomic systems. Now, if Qj is cyclic, then L will not depend upon Qj and delta L delta Qj will be 0. So you are left with delta delta Qj dot, and in place of L I may write T minus V is 0, or delta T, if Qj is cyclic, then delta L delta Qj will be 0. delta qj dot minus delta v delta qj dot is 0. But what is delta v delta qj dot? V is force potential function which is independent of velocity components. So it is 0. So what one implies? ddt of derivative of delta t delta qj dot is 0. And now what is delta t delta qj dot? It is pj. Delta t delta qj is pj, or pj is constant. So you see pj is the momentum corresponding to qj. This implies momentum, rather generalized momentum, conjugate to a cyclic coordinate is conserved. From here you also get one more result. ddt of pj is 0 implies pj is constant. So this is called constant of motion. So one is this result, one result is this one given by A, and another result is this one given by B. Now this result is very important. This is saying that momentum conjugate to a cyclic coordinate is conserved. We are not saying whether that cyclic coordinate, whether the motion corresponding to cyclic coordinate is translation motion or rotation motion. We are just simply saying that momentum conjugate to a cyclic coordinate is conserved. Now we will see that what type of momentum will be conserved. Under what type of motion, what type of momentum will be conserved. So we'll prove two theorems. Theorem 1, if there is a translation corresponding to a cyclic coordinate, the generalized momentum, linear momentum, generalized linear momentum conjugate to the cyclic coordinate is conserved. This is one theorem. What the theorem is stating? It is stating that if there is a translation, your motion may be of, basically it may be of three types, but here I am talking about either of the two types of motion. Either it is a translation or it is a rotation. In this case, in the previous example, this is the translation when your body is moving linearly, and if your body or object, if body is moving like this, like this, like this, or like this is the translation. But if I say that the body is moving like this under the influence of some forces, then this is called rotation. So there may be two types of motion. In first theorem, we are talking about translation, that means simple linear, rectilinear type of motion. So what are we stating in first theorem? That if there is a translation corresponding to a cyclic coordinate, any coordinate is cyclic, and your linear motion, rectilinear motion is corresponding to that cyclic coordinate, then what will happen? The generalized linear momentum, this is the linear momentum, conjugate to the cyclic coordinate. That means the momentum which is corresponding to that cyclic coordinate will be conserved. This is theorem 1. And what we prove in theorem 2? Theorem 2. If there is a rotation, you see the difference between the two theorems. If there is a rotation, this is theorem 2, corresponding to a cyclic coordinate, the generalized angular momentum, again see the difference, angular momentum conjugate to the cyclic coordinate is conserved. So you see the difference between the two theorems. In first theorem you are talking about translation, translation corresponding to cyclic coordinate. In second theorem you are talking about rotation corresponding to cyclic coordinate. In first case, if coordinate is cyclic and there is translation corresponding to that coordinate, your linear momentum will be conserved, generalized linear momentum. While in second case, your generalized angular momentum will be conserved. So we will proceed to find the solutions to prove these theorems. First of all, take theorem 1. For theorem 1, we take the position of a particle in the configuration space. Suppose your particle is somewhere at A. So A is the initial position, and this is specified by Qj, right? So if I join OA, its position vector will be depending upon Qj. Then position vector of A is Ri depending upon Qj. Now let there be a translation motion in the direction of that Qj coordinate and the particle reaches at B. This is not a single particle. This may be a single particle or a system of particle, and naturally this is a system point because we are in configuration space. If the particle reaches at B, it is specified by Qj plus dQj. Position will be changed. So B is this is initial position, B is the position after time t, and it is specified by Qj plus dQj. Then naturally position vector of B will be specified by Qj plus dQj. So what is the translation? Translation is naturally, this is the translation, dQj in the direction of Qj. Let me take n. be the unit vector in this direction. If n is the unit vector in the direction of qj, then what will be your riqj plus dqj minus riqj? This is, you have to take the translation AB. This will be, you will go from A to O and then O to B. So this is nothing but dqj n. Now what is delta Ri delta Qj by definition? It is Ri Qj plus dqj minus Rqj dqj, where dqj tends to 0. And this is dqj n from 2, and dqj is tending to 0. This is simply n. This is a unit vector in the direction of translation. Now, what I have to show? I have to show that linear momentum will be conserved if this coordinate is cyclic. So, first thing is that we will use the condition of cyclic coordinate later. First of all, we know that by Lagrange's equation of motion, delta L delta Qj dot minus delta L delta Qj to be 0. In this, we have shown that ddt of delta L delta Qj dot, you may write it as delta T, because delta V is independent of Qj dot, minus delta V delta Qj, because L is T minus V. इसे हम कह दें Lagrange's equation of motion, as this is the next part of this theorem. And delta T delta Qj 0, T is kinetic energy, and when T is written in terms of generalized coordinate, naturally it does not depend upon Qj, so it is Qj. And delta V delta Qj dot is also 0, because V is the scalar potential function which is not depending upon velocity. So these two conditions will change this Lagrange's equation in this form. This means this delta T delta Qj dot means Pj, and this delta V delta Qj may be written as Qj. Delta V delta Qj is Qj. In some of my previous lecture, I already told you that we may assume this in the form Qj. So you are left with L is T minus V, sorry, this will be plus, and so this will be minus. Pj dot is equal to Qj. You have this relation. This is the second part, when we show that Pj dot may be written in terms of Qj. Now what in the third part? Now we will show that this is the equation of motion for the existing system. What does it mean? I will show that in 5, left hand side represents rate of change of linear momentum in case of translation. And right hand side represent forces causing the translation. Why we will do so? Because we want to show that this 5 is representing equation of motion for this present system, for the system which we have considered for this theorem 1. So this is another part of this theorem. Now how will we show that Pj dot is representing rate of change of what is the law? Rate of change of linear momentum is equal to total force. This is the equation of motion. So basically our aim is to show that 5 is representing equation of motion for the present system, for the system where translation is considered, right? So in Pj dot, we know that Pj is uh, the derivative of kinetic energy with respect to Qj dot. And what is Qt? Kinetic energy, half m v dot square. This is the expression for not v dot, sorry, it is v or the r dot. You will write it as r dot square, where r dot is v. This is r dot I, and it will be naturally summation for I. This will be half m is also mi, twice ri dot delta ri dot delta qj dot. Now you have summation with respect to I, and it is summation mi. Naturally this summation is not working for this ri dot delta ri delta qj, because delta ri dot delta qj dot is delta ri delta qj, which I already proved in some previous article. Now what is this delta ri delta qj? This is delta ri delta qj. This is n from 3. So it is summation mi ri dot n. You may put a dot symbol between the two because n is a vector. Ri dot is also a vector. What is ri dot? It is mi vi dot n. Now what is this vi dot n? Or you say that if I write it as mi vi dot n, then it is mass into velocity, that means momentum, and if it is having a dot product with n, it is the component of momentum in the direction of n. So it is momentum in the direction of translation. This was our purpose, to show that left hand side is representing linear momentum in case of translation. So when it is momentum in the direction of translation, it simply means it is linear momentum. It is linear momentum along qz. So we have shown that the left hand side, pj is nothing but the linear momentum along qj. Now our purpose is to show that Qj is representing force. Now Qj was taken as minus delta V delta Qj, and this delta V delta Qj is nothing but this represents the force, because we write it as minus F I delta Ri delta Qj. This was the expression for Qj, and this is this will be plus of Fi, and delta Ri delta Qj is, here you have summation, it is N. So what is this? Force you take for all I, it will be summation, force in the direction of translation, because it is the component in the direction of translation being dot product by N. Force in the direction of translation. So both of our purpose have been solved. In this expression, this is representing force in the direction of translation, and this is representing rate of change of momentum, linear momentum. So what is next? Using, I think it will be 6, 7. This is 7. So from 6 and 7, equation 5. Pj dot is equal to Qj represents equation of motion for translation. ठीक है, तो हमने ये भी दिखा दिया कि ये इक्वेशन ऑफ मोशन को रिप्रेजेंट कर रहे हैं. नाउ व्हाट इज आवर लास्ट purpose to find in this theorem is that your linear momentum should be conserved. Now what is the condition? That your coordinate should be cyclic. Now if, now condition is that Qj is cyclic. If Qj is cyclic, then delta L delta Qj is 0, which implies delta T delta Qj delta V delta Qj is 0, but delta T delta Qj is already 0, so delta V delta Qj is 0, and this means that Qj is 0. So Pj dot is equal to Qj implies Pj dot is 0 or Pj is conserved, and you have already shown that Pj is linear momentum. So this implies linear momentum is conserved, and this is the linear momentum corresponding to cyclic coordinate. So the generalized momentum conjugate to a cyclic coordinate representing translation, or when there is translation in its direction, is conserved. This is first theorem. Now in second theorem, the statement is that if there is rotation, corresponding to a cyclic coordinate. So we'll consider a coordinate and then we will consider a rotation corresponding to that coordinate. So for that, here our purpose will remain same. In fifth, we will show that left hand side is representing the angular momentum and right hand side is representing the forces causing the rotation. Here we have shown that Qj represent forces causing the translation, and in next article we will show that it is representing the forces causing the rotation. So now in this case we have to take rotation corresponding to a cyclic coordinate. Suppose your particle is at some point A and its position vector is given by r depending upon qj. इसको थोड़ा सा डायरेक्शन थोड़ी ठीक करते हैं इसको. Your particle is at A and with respect to some origin O, let this be Ri function of qj. So initially particle is at A. This is second part. Particle is at A with position vector Ri qj, and after some time it rotates and reaches to some point B. So it reaches to B and it is naturally Ri qj plus dqj. It reaches to B after rotation in time t. So position vector of B is Ri qj plus dqj. Since it is a rotation, so this will have its own plane of rotation, and for this plane of rotation or for the rotation there will be some axis along which there is rotation. So this is the axis of rotation, and let n be the unit vector in the direction of axis of rotation. Join the center of the plane of rotation with A and B. Suppose this angle is theta, then naturally this is your sort of displacement, which is in the form of a curve. And since this position vector is represented by qj, this is represented by qj plus dqj, this angular displacement will be dqj. And now what is this angle? This angle is pi by 2 because this is the axis of rotation and this is the plane of rotation. So whatever vector or the line is lying in this plane will be perpendicular to this. So this will be 90 degree. One more thing which is to be noticed is that in the limiting position when B is tending to A, this BA will be converted into sort of tangent, and that will also be perpendicular to this radius. This is also perpendicular, that is also perpendicular, so both will have the same direction. Both will be represented by the same unit vector n. So when we will talk about the angular displacement, we will use this unit vector n. Secondly, if this angle is theta and this is pi by 2, so what is this length? This length, what is this? Or in terms of vector notation, what will be this? This will be represented by this Ri. This will be Ri sine theta. So we'll write all these mathematical calculations or the values. Here dqj is angular displacement and AB, which you can write it as Ri qj plus dqj minus Ri qj. If I say this to be O dash A, then this is equal to O dash A dqj. What is O dash A? O dash A is Ri sine theta dqj. You may also write AB like the angular displacement. If it is the angular displacement, is equal to Ri cross dqj. Now I write delta Ri. What is the change in Ri with respect to qj? It will be Ri sine theta dqj, or actually I have used this value 6, 7, you say it is 8, and now this is 9, and dqj, where dqj tends to 0. So it is Ri sine theta. So for vector form, you may write it as n cross Ri, right? Now again the same procedure. First of all, since Pj dot is equal to Qj, in this expression we'll show that this Pj dot is representing rate of change of angular momentum, and this right hand side is representing torque, yani moment of force. In previous article, we have shown that left hand side is representing the rate of change of linear momentum, and now we will show that it is representing rate of change of angular momentum. That means we'll write what is Pj representing. We'll first take Pj. Pj means delta T delta Qj dot, like in the previous theorem, and this T is half summation of half mi vi square, or in terms of Ri, I may write it as Ri dot square, right? So it is summation mi Ri dot delta Ri dot delta Qj dot. We'll change this delta Ri dot delta Qj dot as in the previous theorem, and we'll get summation mi Ri dot, and this delta Ri delta Qj is delta Ri delta Qj. What is this delta Ri delta Qj? This delta Ri delta Qj is shown, yes, as n cross Ri. It is n cross Ri. So we'll take it as summation mi Ri dot, and in place of delta Ri delta Qj, it is n cross Ri, and you may put the dot product here because it is a vector quantity, is also a vector quantity. and for convenience I am writing as n cross Ri dot Ri dot, which will again give Mi n dot. If I use the identity over here, using that identity, one part of this expression will be 0 and you are left with n dot Ri cross Ri dot. Other part of the identity will be 0. What is Ri dot? It is Vi. So summation Mi n dot, this is Ri cross, this is V. Now you see what is this Ri cross V? If I write summation n dot Ri cross MIV, this is Vi. You look at this expression. MIVI means momentum, mass into velocity. And if you take its cross product with position vector Ri, then what will become? What will it represent? Ri cross MIVI will be angular momentum. That means it is the movement of momentum. And as you are taking it with n, it will be its component along the axis of rotation. So now we are having Pj is equal to uh, summation n Ri cross Mi Vi. I may put this summation here. It is summation Ri Mi cross Vi. As I told you that this is the momentum, and because it is having cross product with Ri, it is the angular momentum, moment of momentum. So it is the sum of all such type of angular momentums. It is N, let I write it to be Li, where Li is angular momentum. Let sigma of Li is denoted by L. So it is N L. Now this becomes angular momentum about the axis of rotation, because n is representing the unit vector along the axis of rotation, about the axis of rotation. Similarly, we come to Qj. Qj was it was a force delta Ri delta Qj, right? Now what is delta Ri delta Qj? As we as we already shown that it is n cross Ri. You may put dot here, or you may write it as sigma n cross Ri dot F. Now again you will be left with R n Ri cross Fi. I may write n sigma Ri cross Fi. What is this Ri cross Fi? Fi is the force, and Ri, when it is cross product with Ri, it is the moment of force. So n into And what is moment of force? Means torque. Means moment of force or torque. So there is a standard notation for it. Let it be summation of Ni. And for this purpose, I am writing it as N. Now what is N dot N? It becomes torque in the torque about the axis of rotation. So it is representing force corresponding to rotation, and it is representing the angular momentum about the axis of rotation. So in Pj dot is equal to Qj, you may say it represents the equation of motion. So represents equation of motion for rotating system. Now if Qj is cyclic, now we will proceed in the same way as we did in previous theorem. Then Qj, which is delta V, delta Qj will be 0, and so we get Pj dot 0, that is Pj is conserved. So it is the second part of the theorem, or the second theorem, that if some of your coordinate is cyclic and that is corresponding to rotation, that is representing the rotation type of motion, then the angular momentum conjugate to that cyclic coordinate will be conserved. This is all about these two theorems, which are the consequences of cyclic coordinate. Thank you.